Hello everyone, this is Mr. Tickner, and today's video is going to be about these are the terms redshift and blueshift. And we're going to look at these 3 points that come up in the cosmology spec, some of which actually, the first bit potentially should be a bit of revision. Then there's an equation that I'm going to do a couple of examples with, and then we're going to think about what one of the most fundamental things we've seen in astronomy and what it tells us about the universe. So let's take this first in turn. Describe that if a wave source is moving relative to an observer, there'll be a change in the observed frequency and wavelength. You've met this before. This is the Doppler effect. Okay, that you've met before in terms of sound. Okay? And this is a quick little recap. Okay, the idea of that is that if you had something, say a car with a siren, and it's sort of do 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 do, and it's moving towards you, and you are here. I'm going to use a slightly thinner. Let's use a slightly thinner pen because I'm being a little bit. Okay, we're moving towards this. What we find is that ahead of this, as it's moving towards us, we find that the wave fronts bunch up and they get close, and they are closer together. It's not the greatest diagram I've ever drawn. And behind, the wave fronts are spread out more. Okay, and what we hear as an observer, if we're standing here, is that the speed of the wave is still measured to be the speed of sound, but what we hear here is we end up measuring here a shorter wavelength because we're measuring the distance between two wavefronts, and we therefore get a higher frequency. And frequency is the pitch, which is why things come towards you, they sound higher pitch. If you were, however, an observer and you were standing over here, then over here you would measure a larger wavelength, and you would hear a lower frequency and therefore a lower pitch. And this phenomenon, the Doppler effect you met sort of qualitatively, depends on the speed of this car. The faster it's going, the more pronounced the effect. So if someone just walks past you, you don't really notice it. So but if someone is in a car going up, 50, 100 meters per second, it's going really fast, then that's a big chunk of the speed of sound, which is 340 meters per second. So this phenomenon becomes quite noticeable. The equation we're going to meet today, you could actually use this in the context of a sound wave, but we're going to meet an equation which deals with it in terms of light. But this first idea, if a wave source is moving relative to an observer, there is a change in the observed frequency and wavelength. What's important is that you're still measuring the same speed. Okay, the speed is still a same measurement. So you've got v equals f lambda. Okay, the thing is that if one of these goes up, the other one goes down. Okay, so we're going to think about how this can apply to cosmology and to stars. Okay, and that's going to be about this an equation which allows us to measure changes in wavelengths, velocities of galaxies, speed of light. So we can actually work out how fast things are going to look at them. But in order to understand that, we have to know what it is we're looking at. So let's imagine that we look at the sun. Okay, so if we look at the sun, you put the sun's light through a prism. Okay, so you have white light coming in. Okay, you split it up by using a prism, so you're going to get refraction and refraction. And you might think, okay, so I know what happens here is I get the spectrum of light, and I would get, because of the way I've done this, I'm going to get red, and I'm going to get orange, and then I'm going to get maybe yellow, and then I'm going to get green, and I'm really going to go slow. We get a spectrum. Okay, so we get white light gets split up into the 7 colors of the spectrum, Roy G. Biv. That's something you've met before. However, it turns out if we look at the sun, we do this with the sun, we look really carefully at the spectrum, we don't see this lovely unbroken spectrum. We actually see this. This is the sun's light when looked at really carefully. And what we find is we find gaps. Okay, so we find weird little bits that are missing. Okay, so for example, there's one here, there's some here, there's some there, there's stuff there. So these are little lines, and they have a fancy term. Okay, they are called absorption lines. This is not something you need to know for the GCSE, but what's happening is that the sun is not purely made out of, just purely made out of just hydrogen and some helium. It's got other weird elements in its atmosphere, right at the edges where the sun's a little bit cooler. And what happens is as light travels through these different elements, bits of light get absorbed. Okay, and in a similar way to the fact that ultraviolet radiation doesn't travel through glass, but invisible light does, in this, there are some elements in the outer layers of the sun which absorb light, particular wavelengths of light as it travels through. And then when we try and look at it, we see those things as missing. So we see the whole spectrum we would expect, but with these little lines. Okay, and this represents elements. Okay, so they can tell us the elements in the outer layer of a star. Okay, and these lines are on every single star. Every single star will have different lines based on the elements that's in it. A star that's really old and has only got hydrogen and helium will only have lines that correspond to hydrogen and helium. Our star is a second generation star. It's quite metal rich, so there's lines there representing iron and calcium and various other things. And so what happens is we can look at these lines. These are actually going to be the things that we're going to look and see them moving. This is obviously quite an awkward thing, but we can actually look. It's kind of how this gets like a bit simplified. These are called Fraunhofer lines. They're to do with the spectrum. So we've got part of the visible spectrum. This is backwards compared to how you've probably seen it, because we've got UV, X-rays, gamma rays at this end, and we've got infrared and the radio up in this direction. That's because we're looking at increasing wavelength. So this is sort of a chart with, lambda is increasing as we go left to right. So we're dealing with in terms of wavelengths, and we get these lines. And so these lines, actually, these Fraunhofer lines, they represent different things. And there's a little key down the bottom here that tells us what things are. So, for example, line C is due to hydrogen, and there it is. Okay, here's a line. It's due to hydrogen. It's 656.3 nanometers, which is a nanometer is a billionth of a meter. Okay, there's some other ones. There's D and E are both due to iron. So there's and it's little d and little e, isn't it? So we've got little d and little e. So there's that one there, and these are due to iron. So just put a little chart here. So that's iron, that's iron, that's hydrogen. And so some of them are due to some bonding. So we've got oxygen. So A is due to oxygen as a molecule, apparently. So these are things that allow us to look at a star and say, oh, okay, what can we see? What elements are present in the sun? And actually, as an interesting aside, the one which is worth highlighting, if it's listed here, it is not listed here, is helium. Helium is called helium because it was first seen in this chart. And it was thought that helium did not exist on the planet Earth because it's a noble gas and it floats away. So how the colorless, odorless, unreactive thing that floats away whenever you try and have it. So it was originally called helium because it was first found by looking at the spectrum of the sun. And it wasn't for quite a long time, but people then found it on the surface of the Earth. So a couple of things that we have. So we have, this is a fingerprint of the elements inside a star. And what this allows us to do is to track how these lines behave on different stars when we look at them, or different galaxies. And the ones that we tend to look at actually are the ones to do with hydrogen, because we know that every single star that exists in the universe must have an absorption line at 656.3 nanometers, because it must have hydrogen in it, because that's the composite of all stars. There must be hydrogen. And this line here, 656.3 nanometers, this is a line that we can look at. And we can try and look at this like the Doppler effect. We can try and look at this in different situations and find out, has it moved? Maybe it's moved that way. Maybe it's moved that way. Because if that point of light is moving relative to us, when we measure it, we won't measure it at 656.3 nanometers. We might measure the wavelength to be a bit larger. Okay. if the thing is moving away from us. We might measure the wavelength to be a bit smaller if it's moving towards us, because that line is going to behave in exactly the same way as the Doppler effect. So this philosophy here is going to be true here. And this is ultimately what we do, is that we tend to look at stellar spectrum. Okay, so this is a star that's at rest. Okay, we have a certain number of lines. Okay, and these diagrams in an exam will always be simplified. There's only ever going to be a few lines on there. There won't be very many. It certainly won't look like this, because that's a nightmare, and so is this. So it's going to be a simplified idea, and if this is the rest, so this is the sun, we're not moving really that much from Earth to the sun, we can sit there and say, oh, okay, where have these lines gone? Have they all gone slightly that way? Okay. Have they moved in this direction? Have they moved towards the red end of the spectrum? Okay. If all these lines move in this direction, then we say this thing is redshifted. Okay. Now remember, this is the bigger wavelength end. Okay. The wavelength has increased if this has happened. And if we think about the Doppler effect and our diagram here, that means that we're this person here. This source is moving away from us because the wavelength has gone upwards. Okay. And this is what we talk about when things say redshifted. Everything's shifted towards the red end, which means things are moving away. The other thing that we can see, however, is we might see, and if this line is, let's just quickly draw a ruler down so we can see this line here. We might say, oh, look, okay, so here's our line straight down. Okay, and look, our line is now, the matching line is now there. Or if we were looking at this one here, okay, we've got a matching line is now down here. So if I can try and get this neat, yeah, so our line has essentially moved in this direction to there. Okay, it's a subtle movement, but that has definitely moved in that direction. And this means that all these lines have moved in this direction. And this is what we call blue shifting. So happens if stuff moves that way, we call it, this is the blue end of the spectrum. So this is blue shifting. And this is where we're basically getting a smaller wavelength. Okay, so these lines are measured at a slightly smaller value than we were measuring beforehand. And if we return to our Doppler shift idea, well, that means that we are this person here. Shorter wavelength, shorter wavelength, things are moving towards us, redshifting, longer wavelength, things are moving away from us. Okay, so we can look with incredible accuracy at these things, and we can measure these things to fractions of a nanometer, okay? And we can find out have they increased and have they decreased. And what this allows us to do is to work out which way things are going, okay? If the wavelength has become bigger, we know it's going away from us. If the wavelength has become smaller, we know it's coming towards us. But it also allows us to calculate how fast it's going, okay? So this is the equation that we have, is that there's the change in wavelength over the reference wavelength. So this is what we'd measure if we're looking at the sun or in the laboratory. This should be the true wavelength it should be, is equal to the speed of the galaxy over the speed of light, okay? And so we're going to, let's see this sort of in, let's see this in action. Okay, let's do a little calculation. I'm going to work through this on my calculator, and let's do this. So let's have this, let's just quickly note the idea. So, so when we look at stellar spectra, the lines maybe, and this is how, so red shifted. Oh, sorry, they will be, because this is not a may, this is a will. Red shifted if the star or galaxy is moving away. It will be blue shifted if it is moving towards us. Okay, so this is the idea. Okay, but allows us to calculate it. So the speed, or so the greater the speed, the greater the effect. So let's do an example, and we're going to use this equation to solve a problem. And we're going to think, let's say we're looking at a star, okay, and it has, what we've happened is this thing has moved this line, okay, so this line here, which is 656.3 nanometers, and we're going to shift it by 0.1 nanometer. Okay, so it's going to become longer by 6 to 656.4. Okay, that's all we're going to do. Okay, so let's have a look. Quick example. Okay, so the spectra is measured in the lab of the sun. Oh, sorry, let's change that slightly. Of the sun. At 656.3 nanometers, a star has a line at 656.4 nanometers. How fast is the star going? Okay, so what we want to use is we're going to use this is the equation that we end up using, is change in the wavelength over the original wavelength. Now, what's this? Just check the. I want to make sure they use lambda 0, which is original, as in like what it should be before any shifting happens. Okay, is equal to V over C, and so just to find these terms, that's the change in the wavelength. This term here is lambda from the sun, or if you were to set the whole thing up in a lab and say, right, okay, what is the true reference wavelength? V is the speed of the star, and C is the speed of light. And you have to get given the speed of light in somewhere in the question for you to do this. It is 3 times 10 to the 8 meters per second, or 300 million meters per second. Okay, so essentially this is a fairly nice sort of thing. We've got a change in wavelength, we've got an original wavelength. We want V. So what we can do is we can put in our sort of numbers and work it out. So change in wavelength, well, it's that minus that. So I'm going to do this properly. So I'm going to do 656.4 minus 656.3 divided by, now this is the key question. This is where it sometimes goes wrong, is what is your reference wavelength? It is the one that you've measured from the sun because you're not moving relative to the sun, or if they say in the lab it's measured at, and so they say 656.3. This is the one we want. Okay, is equal to V over 3 times 10 to the 8. And so you might think, do I need to convert out of nanometers? You don't. Because you've got nanometers on the top and nanometers on the bottom, they will cancel out. That's perfectly fine. So you don't need to do any calculations of that. So what we end up with is 0.1 over 656.3 is equal to V over 3 times 10 to the 8. So we could therefore say that 0.1 times 3 times 10 to the 8 over 656.3 is equal to our speed. And I haven't worked this out in advance, so I'm going to have to start it into my calculator. So we've got 6.3, and I've got 45,711. So I've got 45.7 so 700 meters per second. So it's going pretty fast. For a 1.1 nanometer shift, this thing has to go pretty quickly. And that's how the equation works. So I want to do a second example. Let's say we know the speed and we want to know the new wavelength. We want to know a new wavelength and we've got a different speed, but we know that we're expecting speeds of a lot. Okay, this is still very fast. The fastest, this is faster than pretty much anything that's been man-made. Okay, and this thing is going away from us because it's gone larger. So let's pick another line from this. What's one of the hydrogen lines? We've got 486.1, which is line F. Where are you? Line capital F. Okay, this one here. So 486.1. Let's use another hydrogen line. So let's use this one. And let's say we're going to shift it, but we're going to have something which is going to be moving away from us. And let's say it's moving at, let's say 90 kilometers per second. What did I say it was? 486.1. Okay, cool. So let's do another example. Okay. So example 2, a star and let's say it's going to move towards us. Okay. Okay, 90 kilometers per second. So what is, we're moving towards it 90 kilometers per second. What is the wavelength of 486.1 nanometers measured as okay, so I've set this up. It's not the cleanest language I've used. We've got something moving towards us, so we've got V. We've got this is our reference wavelength, lambda 0, and we want to know. Okay, well, we think it should be 486.1 if it was stationary, but what would we measure it as being? So let's think about putting this in. So we've got change in wavelength over lambda 0 is equal to V over C. So we can say the change in wavelength over 486.1 is equal to 90,000 over 3 times 10 to the 8. So we have a change in wavelength of 90,000 times 486.1 over 3 times 10 to the 8, so 300 million. So what do we get from there? So work this one out. So we've got 90,000 times 486.1 over 300. I have 0.1458, so I'm going to go with 0.15. Okay, so I've got 0.15 nanometers. Okay, so that is how much it shifted. Okay, now I have to give a little bit of consideration as to the final bit. I've been told it's moving towards us. Okay, that means it's going to be blue shifted. Okay, which means that my wavelength is going to be smaller. Okay, because it's coming towards us. As it's moving towards us, the light is blue shifted, so the wavelength decreases. So what we would measure we measure 486.1 minus 0.15, so we measure 485.95 nanometers. Had it been going away, it would have been, this minus would have been a plus because it would have been redshifted, and we would have measured 486.25. But that is how we can do these calculations. Just important to remember that this change in wavelength is the difference of things. So there we go. That's kind of 2 examples of using this as an equations calculation. Now, final thing to be aware of is what this last bit means. Describe the redshift in light received from galaxies at different distances away from the Earth. So one of the things that was done a long time ago by this chap is called Edwin Hubble, which is a great name. Okay, is he looked through his telescope, okay, and he decided to look at different galaxies. Okay, this is what he did. That's a terrible galaxy. I mean that one. So he decided to look at different galaxies. Okay, so he looked and did the same thing, and he measured the speeds of all the galaxies that he could find at certain different distances. So he collected how far away are they. So he measured that using the work of a woman called Henrietta Leavitt. He measured their distance, and he measured their speed. Are they coming towards you? Are they going away from you? What are they doing? And he found something really rather peculiar. No matter where he looked, once he crossed a certain threshold of the local group, which is the galaxies that are really, really close to us, like Andromeda, he found out that basically everything, the light from every single thing was redshifted, which told him that everything is moving away. But not only that, the further away a galaxy was, the more it was redshifted. And so this kind of became this weird sort of thing. So if I've got these galaxies here, if I have a galaxy up here, which is well beyond his own name, it's much further away, and so it's moving much, much, much faster. Okay, and this is the work. This is what Edwin Hubble realized, and we'll have a think about what this means in the next video. But Hubble realized that everything was moving away, which is, if you have a universe that is static, or that things are moving randomly, well, then you would expect some to be blue shifted, some to be red shifted. But he found that everything was red shifted, and it lent itself actually to a very, very nice graph. This is the same data he plotted. He could measure to a distance of about 2 megaparsecs. So that is about 2 million parsecs. A parsec is 3 light years. So he had a fairly good distance. And although there's a bit of scatter around this line, it's quite clear that this galaxy that's up here is going much further away, moving faster away than it is than these galaxies here. Not very many of them are moving towards us. And this is data that keeps getting repeatedly examined, has been refined over a long period of time. This is some data from 2001, which goes up to 20, 22, 24 megaparsecs. So more than 10 times further away. And again, we're still seeing everything moving away from us. There's uncertainty and there's error, but essentially what Hubble realized is that pretty much every galaxy was redshifted, and the further away the more they were redshifted, which meant that they were moving away faster. And as we'll see, this became a critical piece of information for proving that the universe is expanding and that there was a beginning point, which became known as the Big Bang. So this is kind of a bit of data. So when we look at distant galaxies, and looking at a galaxy is no different to looking at a star, because they're just galaxies that are made of stars, and so they're all got hydrogen in them. We find they are all redshifted. So the further they are, the greater the distance, the greater the redshift. So more distant are moving so everything is moving away from us. But the further away they are, the faster they're moving, which is how they got to be further away. So the redshift of galaxies would prove not prove, so be a critical piece of evidence. Piece of evidence for the Big Bang theory and the expanding universe. Because no matter which way we look, the universe, everything's receding away from us. So the universe is expanding. And as Hubble kind of worked out, you can wind the clock back. If you wind the clock back and everything's moving away from you, eventually they all bend up on top of you. And that time in the past, that is the point in history that we call the Big Bang. But we'll see about that in the next video.